So before I actually get into kind of solving this problem and problems for the future, I kind of want to explain a little bit of the idea behind starting this channel. Right now we're in kind of an interesting situation, interesting climate with the whole situation with coronavirus going on, and this kind of led to a lot of people having to leave their colleges prematurely, and graduation being canceled, job offers being rescinded. So it's kind of a bad and weird situation, resulting in a lot of people kind of having to sit at home, writing this whole situation out, waiting for everything to kind of resolve itself. So I kind of figured I've always wanted to kind of do something along the lines of explaining problems and helping people understand concepts that I know took me a while to get. So that's kind of why I decided that maybe starting a channel would be a good idea right now. But yeah, with that being said, let's just go ahead and get right into the problem. So I figured the best way to start would be to look at a problem that most often most engineers have probably seen this, or at least heard of it. This problem is called Two Sum. And basically, I don't really like the explanations that Leetcode provides, so I'm going to go ahead and explain the problem myself. So, given this integer array, nums, which currently in this example contains 2, 7, 11, and 15, it may not necessarily always be these values. It could be a larger array, it could be smaller, it could be empty. Given this integer array nums and this integer called the target, we're looking for two distinct integers from nums, so not at the same index, so repeats are not allowed here, whose sum is actually equal to this target value. So on first glance, it seems like a pretty simple problem. In this example specifically, they've kind of said here that num0 plus nums1 is 2 plus 7, which is equal to 9, right? So because we're looking to return the indices of the two numbers that sum to our target, we would want to return 0 and 1 as an integer array of size 2. So I'm going to kind of run you guys through three different ways of approaching this problem. And each one will consistently get faster and more intuitive, and kind of utilize these neat tricks and data structures that we can use to solve these kinds of algorithmic questions. And I hope that these explanations are good. Obviously, any feedback is good feedback, so please feel free to leave comments or message me personally to let me know how I can do better. But with that being said, let's go ahead and get into the first solution. Okay, so let's take a look at the kind of first solution here, the first approach we can use. Um, so when you're typically answering these kinds of interview questions, more often than not, you're gonna have a brute force solution that can solve this problem. And it's typically going to be the worst solution you can produce that works. It's not usually going to be what an interviewer wants to see, but I will say that it most often serves as a very good starting point to kind of build your more optimal solutions off of. So with that being said, let's kind of just take a look at how we can brute force our way through finding two values in a one-dimensional array that sum to a certain target value. So I've got this little visual set up here where we have these 2 pointers, right? So given that we have these 2 pointers and we're kind of going to brute force our way through a one-dimensional array, a lot of you might already be saying to yourselves, okay, nested for loop. So a nested for loop is a loop that has an outer loop which kind of holds one pointer constant, while an inner loop inside of that outer for loop traverses another pointer through the remainder of the array. So basically, this is a way to make every possible comparison between two distinct integers within the array. And we're going to use indices I and j to kind of represent these 2 pointers that are going through the array. We'll let I be this blue pointer right here and j be this green pointer right here. So in this example, we have this array of 4 elements with 4, 1, 7, and 8. So right off the bat, we see that 1 and 8 can produce an answer for us. So that's going to be indices 1 and 3 because we index from 0. So if we actually think about how we can brute force through this one-dimensional array, it's actually quite simple. What we're going to do is we're going to have our nested for loop, and we're going to start I from 0, and we're actually going to start j from I plus 1, because we want to compare distinct integers, right? We don't want to start j from 0 and compare. Remember how I mentioned earlier that we can't really use repeats? So even though that wouldn't produce the solution we want, it just kind of also cuts down on our runtime. So if we start j or I from 0 and we start j from I plus 1, that's going to start j at 1, right? So the idea is we want to step j through the rest of this array while we hold I in a constant position until j has reached the end of the array. Once j has reached the end of the array and we've made all of our comparisons between this I and the rest of the j's, and we've kind of decided that we haven't found this target value yet, that's when we're actually going to go ahead and increment I. So now I becomes plus 1 from where I was at before. And like I said earlier, we're going to start j at whatever I plus 1 is. Because if you notice, if we were to start j from 0 in the inner loop, then we're actually going to be making a duplicate comparison that we've already made before when we first started our traversal. And that's just going to add unnecessary runtime and operation. So for the sake of this problem, we're going to go ahead and start j from I plus 1. So the same idea here, we keep I and we run j through whatever is remaining in the array. We say, okay, now we have 1 and 8, we take that sum, and that's equal to 9, right? So now we found indices 1 and 3 are what we're looking for. So if we were to, say, have a different target that could not be made by any values in this array, then at this point we would not have a hit, so we would move I one more, and j wouldn't have anywhere else to go, and we don't really want I and j to be the same value, so this is just going to end and terminate right here. So that's kind of the intuition behind the brute force solution. Now we can kind of implement this in code just to see how it works. So the brute force solution is really quite simple. As I mentioned earlier, we're going to utilize a nested for loop, and inside of that nested for loop, we're just going to do a simple check to see if the two indices, the values at those two indices in nums, if their sum is equal to the target value, and if it is, we're going to return a new integer with the two indices. Otherwise, we're going to have a default exit case after the entire nested for loop has finished iterating through everything. So the way that's going to look is we're going to have this outer loop, which, as I mentioned, we're going to use I and j for our purposes. And like I mentioned earlier, we're going to start j at I plus 1. And this is what our nested for loop is going to look like. So now inside of here, we just need to check something really simple. We just say if nums I plus nums j is equal to our target value, and we want to return a new integer array of size 2, remember what I said, with I and j. Otherwise, we want to default to 0, 0, because as I mentioned earlier, we need to return two distinct indices, and if we just return 0, 0, then that kind of acts as an exit case because I don't want to say it violates the problem statement, but it definitely, it's just an easy way to say, okay, there were no matches found. So if we go ahead and run this, you're going to actually see it works, but it's really slow. So it's only faster than 32% of submissions. So like I said earlier, if you produce this in an interview, an interviewer is probably not going to be happy if this is your final solution, but this can obviously serve as a building block for a more optimal solution. So definitely think about ways that you can kind of work with the concept behind this to kind of improve your runtime and maybe even your space complexity. So as far as the analysis of this algorithm goes, this is going to be an O of n squared solution because in the worst possible case, we are running a double for loop through nums, and we're going through nums.length. So it's going to be nums.length squared operations. And as far as space complexity goes, this is going to be constant space because we have not used any external data structures. So that's good. But let's kind of take a look at the next algorithm, which can kind of improve our runtime on this. Okay, so here we kind of have our second approach to the two-sum problem. I like to call this the better solution because it is significantly better than the brute force, but it is still not the best solution that we could produce for this problem. So the idea behind this solution is we're not guaranteed that the nums array that we're given is actually sorted. So if we were able to sort this array, we can kind of take advantage of the fact that the values will be ordered in ascending order. meaning the smallest values will be towards the left and the largest values will be towards the right. And what I mean by this is, if we have this array, this example, 2, 15, 11, 7, currently not sorted, and we have a target value of 18. If we were to sort this array, then we get the resulting array. We can take temporary sums starting with the beginning and end, and based on whether that temporary sum value is less than, greater than, or equal to our target, we can actually shift these pointers in the respective direction so we can kind of zone in on this target value. And as we get closer and closer, or as we get a hit, this algorithm is going to be way more efficient than the brute force algorithm. So as far as, actually kind of looking at the runtime of this algorithm, for those of you who kind of know, the runtime of sorting algorithms, most often the standard sorting algorithms that we use are going to be O of n log n. So definitely faster than O of n squared. And in this kind of a solution, that is going to be what consumes the most runtime for solving this problem, because once we use this pointer solution to kind of find our two indices, that's going to be a linear scan. So our worst case runtime for this kind of a solution is going to be O of n log n. So the idea is, if we look at this example, we take 2 plus 15, we get 17, right? So 17 is smaller than 18. We can take advantage of the fact that the next value to the right of the minimum is going to be either greater than or equal to this minimum value. So it could be 2 or it could be something greater. So we can kind of shift this pointer over here because we know that this value is guaranteed. This temporary sum between nums1 and nums3 is going to be greater than the temporary sum of nums0 and nums3. So now we kind of take a look at whatever the value of this temporary sum is. We see we have 7 plus 15, which gives us 22. So now we're too big. So since we're too big, we can take advantage of the fact that we can move the largest pointer down because the value to the left of the max is guaranteed to be less than or equal to the value of the max. So if we move this pointer down, now we have 7 and 11. If we add those together, then we get 18. So we found our answer, but the problem comes here, which is that we have made a modification on the ordering of these values from the original array. The problem statement asks that we should return the original indices of these values. So we're kind of going to need to use some kind of external data structure, maybe a map or a set of some sort, to kind of keep track of the indices of these values so we don't lose them after we performed our sorting operation. So that is going to give us a space complexity of O of n, because we're going to be using some kind of external data structure to store those indices. So I'm not actually going to code the solution up. If you kind of understand how to use a while loop and move two pointers from the beginning and end closer to each other based on some kind of arithmetic, the solution's really easy to implement, and it's pretty intuitive, and like I said, it's much faster than the brute force solution. But yeah, like I said, this is still not the best, so I have one more solution which will kind of put these other two to shame, and you guys will see why. So let's go ahead and explain that one. So we made it to the last and best solution for the two-sum problem. So this problem is going to utilize a data structure called the hash map. And what the hash map does is it acts as a key value store where unique keys will hold any kind of value based on the data type you specify. And it's really neat for kind of checking to see values you've seen in the past or values you'd like to have seen in the past. And we're going to kind of take advantage of this fact for the solution. So the solution uses a neat trick. And basically, it's going to use something that I'm going to define as the complement. So what is the complement? If we take a look at each value in this array here, the complement is going to be the value that each of these needs to be summed with to get our target value. For example, 2's complement would be 6, because 2 plus 6 would be 8. 3's would be 5, 14 would be -6, and 6 would be 2. So what we're going to do for this algorithm is we're going to step through this array. So it's going to be a one-pass linear solution. And we're going to check to see if our map currently contains this value, nums I, that we're looking at. And if it does, then that means that we have already seen the complement of this value in the past, and that we found our answer. We found our two indices. So if we don't find that, if we say that map.get this nums I is equal to null, then we're going to actually put into our map the complement of this value along with the index of what this value is currently at. So if we're at 2, because we're at the beginning of the array and our map is currently empty, we would put 6 mapping to 0, so key 6 value 0 into our map, because 6 is the complement of 2 and 0 is the index where we saw 2. And we were going to keep going. Same thing for 3. We'll put 5 and 1 because we're at index 1 and 5 is the complement of 3. For 14, negative 6 because that's the complement and index 2. And for 6, when we do map.get 6, we'll see that when we were at 2, we put the complement of 2 into the map already. So when we do map.get 6, it's not going to return null, it's going to return 0, which is the index of the previous complement we saw to 6. So now we actually have not only the index of the other complement, but we're currently at the index of the other value, which is great, which means that we can just return whatever map.get nums I equals and the current index that we're at I. So it's a really, really simple solution. It's very fast, and you guys will kind of see that. So let's go ahead and actually code this one up. Let's kind of take a look at how we can actually implement this solution using the hash map and linear scan, one pass through nums. So like I said, we're going to need a hash map, right? Which is our external data structure. And this is going to take an integer mapping to an integer, because we're storing the complement as the key and the index as the value. And both of those are represented as integers data types. So like I said, this is a single pass algorithm. So all we need to do is just iterate through nums one time. And inside of this loop, we're going to do a little check. We're going to say if map.get, the value we're currently at in nums is not equal to null. So something exists there. Some index exists there. Then we're going to return a new int with map.get whatever was at nums I, because that is the index of the complement, and the index we're currently at, which is I, in the loop. And otherwise, if that does return null, meaning that we have not yet seen that as a complement, we can just put that as a complement into the array along with its index. And just like the other solution, if we make this full pass through nums and we don't find a target hit, we just need to default to 0, 0 again. So as you can see, the solution is actually not that much longer in terms of lines of code than the brute force solution. But if we go ahead and run this actually, see, there you go. It's faster than 99.9% of all submissions. So I think if you were to produce this in an interview, kind of building off of that brute force solution, they would probably be pretty happy to see something like this. So definitely taking advantage of these awesome data structures that have been maintained in these languages can really help you to increase and improve your runtime. And as far as space complexity goes, this is gonna take O of n space, because we are using an external map to kind of, in the worst case, store all the complements along with their indices. But in industry, you'll kind of notice that time complexity is valued very highly. How fast an application is. Because if you think about going back to the brute force solution in the O of n squared runtime, imagine that you have an array or vector of 1,000,000 elements. That, in the worst case, is going to take 1,000,000 squared operations to find the two integers that sum together. Whereas this, being an O of n solution, a linear solution, is going to take at most 1,000,000 operations. So you can imagine that 1,000,000 squared and 1,000,000 are two vastly different numbers. So obviously this solution is probably going to be much more widely accepted. So yeah, I hope that I did a good job of explaining these 3 different approaches to this problem. I hope to keep producing some more content, and this was just kind of a starter problem, so I do plan on covering some more difficult concepts and algorithms. But yeah, please let me know how I did for a start. And like I said earlier, feel free to message me, to leave comments. I had a lot of fun making this, so yeah, thank you guys for watching.